Tonight, we're going to explore something that can quietly change the way you see your place in the universe. We're going to discover just how small Earth really is. Not by comparing it to the Sun or to Jupiter, but by looking at the true scale. The kind of scale where Earth almost disappears. Because Earth isn't just small. It's so unimaginably tiny that language itself starts to struggle. By the end of this journey, you'll see our planet and yourself from an entirely different perspective. Before we begin, if you enjoy these slow explorations of space and cosmic scale, a simple like or subscribe truly helps this channel grow. It's a small gesture, but it makes a real difference. Now, let's begin. Let's start with Earth itself. Our home, the planet beneath our feet. From the surface, Earth feels enormous. You could spend your entire life traveling and still never see every corner of it. Continents stretch for thousands of miles. Oceans cover about 71% of the surface. Mount Everest rises nearly 30,000 feet into the sky. To early humans, Earth was everything. It was the entire universe. The sky above was a dome filled with lights, and the ground beneath seemed flat and endless in every direction. Based on what they could see, that understanding made perfect sense. When you look toward the horizon, the curve of Earth is far too subtle to notice. Earth's diameter is about 7,926 miles. If you somehow walked around the equator, walking on water at a steady pace of 3 miles per hour, 8 hours a day, it would take you just over 3 years to complete the journey. That's a long walk. From a human perspective, Earth is genuinely large. The surface area of Earth is about 197 million square miles. To put that into perspective, if you spent just 1 second standing on each square mile, it would take more than 6 years of non-stop travel. The United States, one of the largest countries on the planet, covers only about 3.8 million square miles, less than 2% of Earth's total surface. But here's where the perspective begins to shift. As soon as we zoom out, Earth starts to shrink, not physically, but in significance. It stops being everything and becomes just one thing among many. And as we continue pulling back, it becomes smaller and smaller until it's almost impossible to see it all. Our first stop beyond Earth is our closest neighbor, the Moon. The Moon orbits Earth at an average distance of about 238,855 miles. That's roughly the distance you'd travel if you drove around Earth's equator 9.5 times. It's far by human standards. When Apollo astronauts traveled there, the journey took about 3 days. The Moon has a diameter of about 2,159 miles, around 27% of Earth's diameter. If Earth were the size of a basketball, the Moon would be about the size of a tennis ball. But what's truly striking isn't the Moon's size, it's the distance between us. The gap between Earth and the Moon is about 30 Earth diameters. You could line up 30 Earths side by side in the empty space between them. Most images you've seen show Earth and the Moon much closer together than they really are. In reality, there's a vast amount of nothing between us and our nearest companion. This is our first real hint that space is mostly empty. Even in our immediate neighborhood, the distances between objects are enormous compared to their size. The Earth-Moon system is actually unusual. Our Moon is large relative to its planet, so large that Earth and the Moon are sometimes described as a double-planet system. The Moon's presence matters. It creates the tides that shape our coastlines and help stabilize Earth's axial tilt. Without it, Earth's climate might swing wildly, making complex life far more difficult, perhaps impossible. From Earth, the Moon appears about the same size in the sky as the Sun. This is pure coincidence. The Sun is about 400 times larger than the Moon, but also about 400 times farther away. That coincidence gives us total solar eclipses, where the Moon perfectly covers the Sun. The Moon is slowly drifting away from Earth, about 1.5 inches every year. Billions of years ago, it was much closer, and a day on Earth may have lasted only 5 hours. For now, though, it remains our constant companion. And in 1969, humans stood on its surface for the first time, proof of what we can achieve when we push beyond familiar boundaries. Now, let's turn our attention to the Sun. The Sun is the reason we exist. Without its light and heat, Earth would be a frozen rock drifting through space. But it's also where Earth truly begins to fade in comparison. The Sun's diameter is about 864,000 miles, 109 times wider than Earth. Its volume is so vast that roughly 1.3 million Earths could fit inside it. Everything that has ever happened on our planet, every ocean, every city, every life, has unfolded on a world that occupies less than 1 millionth of the Sun's volume. The Sun contains 99.86% of the mass of the entire solar system. All the planets, moons, asteroids, and comets combined make up the remaining fraction. Earth orbits the Sun at an average distance of 93 million miles, 1 astronomical unit. Light takes about 8 minutes and 20 seconds to cross that distance. If the Sun vanished, We wouldn't know for over 8 minutes because its light would still be on the way. At highway speeds, it would take 176 years to travel that distance. Even the fastest spacecraft ever built takes months to approach the sun. And yet, the sun itself is an ordinary star, a middle-aged, yellow dwarf, about 4.6 billion years old, with roughly 5 billion years of fuel remaining. Every second, it converts 600 million tons of hydrogen into helium, releasing more energy in 1 second than all of human civilization has produced in its entire history. The sun's surface reaches about 10,000 degrees Fahrenheit. Its core burns at nearly 27 million degrees. Solar flares and massive eruptions occasionally send waves of energy toward Earth, creating auroras and sometimes disrupting our technology. For most of history, humans believed Earth sat at the center of everything. It took thinkers like Copernicus and Galileo to reveal a humbling truth: Earth orbits the sun. That realization was our first lesson in cosmic humility. From here, our journey continues outward, past the inner planets, the asteroid belt, the gas giants, the frozen edges of the solar system, toward distances where Earth becomes little more than a speck. And we're only just beginning. Liquid water can no longer exist on the surface of Mars. It either freezes solid or evaporates into the thin air. Today, Mars has an average surface temperature of about minus 80 degrees Fahrenheit. In the summer, temperatures near the equator can briefly rise above freezing, but at the poles, winters plunge far colder. The problem isn't just temperature. Mars's atmosphere is incredibly thin. The surface pressure is less than 1% of Earth's. So what happened to Mars? The planet is smaller than Earth, which means its gravity is weaker and less capable of holding onto an atmosphere. But the main reason Mars lost its air lies deeper within the planet itself. Mars lost its magnetic field. On Earth, our magnetic field is generated by the motion of molten iron within our planet's core. This field surrounds Earth like an invisible shield, deflecting the solar wind. A constant stream of charged particles flowing outward from the sun. Mars once had a similar magnetic field, but over time, its core cooled and solidified. When that happened, the magnetic field shut down. Without this protection, the solar wind slowly stripped Mars of its atmosphere, particle by particle, over hundreds of millions of years. What was once a warmer, wetter world gradually became the cold, dry desert we see today. Mars has 2 small moons, Phobos and Deimos. Phobos, the larger of the two, is only about 14 miles across. It orbits extremely close to Mars, so close that it completes 3 full orbits every Martian day. Phobos is slowly spiraling inward. In about 50 million years, it will either crash into Mars or be torn apart by tidal forces, forming a faint ring around the planet. Between Mars and Jupiter lies the asteroid belt. It contains millions of rocky objects, yet the combined mass of all these asteroids is less than 4% of the Moon's mass. Despite how movies portray it, the asteroid belt is mostly empty space. If you flew through it, you likely wouldn't see any asteroids at all unless you aim directly at one. The largest object in the asteroid belt is Ceres. It's round, shaped by its own gravity, which is why it's classified as a dwarf planet. Ceres is about 588 miles across, roughly the width of Texas. When NASA's Dawn spacecraft visited Ceres between 2015 and 2018, it discovered evidence of a subsurface ocean. Ceres may contain more fresh water than all of Earth's lakes and rivers combined. Now we reach the giant of the solar system. Jupiter dominates the outer planets. Its immense gravity shapes the orbits of comets and asteroids throughout the solar system. In many ways, Jupiter acts like a cosmic vacuum cleaner, capturing or deflecting objects that might otherwise collide with the inner planets. Some scientists believe Jupiter's presence helped make Earth safer, reducing the number of catastrophic impacts and allowing complex life to evolve. Jupiter's most famous feature is the Great Red Spot, a storm larger than Earth that has raged for at least 400 years. Winds at its edges reach speeds of about 400 miles per hour. The storm is slowly shrinking. A century ago, it was about 3 times wider than Earth. Today, it's closer to 1 1/3 times Earth's width. If this trend continues, the Great Red Spot may eventually disappear. Jupiter has at least 95 known moons, with more still being discovered. The 4 largest, called the Galilean moons, are worlds in their own right. Io is the most volcanically active body in the solar system. Europa hides a global ocean beneath its icy crust, an ocean that may contain more water than all of Earth's oceans combined. Ganymede is the largest moon in the solar system, even bigger than Mercury. And Callisto is ancient and heavily cratered, preserving a record of the early solar system. Saturn follows Jupiter, instantly recognizable by its spectacular rings. These rings are made of countless particles of ice and rock, ranging from tiny grains to objects the size of houses. The rings stretch tens of thousands of miles from Saturn's surface, yet they are astonishingly thin, often no thicker than about 30 feet. Scientists still debate the age of Saturn's rings. They may be as old as the planet itself, or they may be relatively young, formed when a moon was torn apart by Saturn's gravity. Saturn has at least 146 known moons. The largest, Titan, is bigger than Mercury and has a thick atmosphere, denser even than Earth's. Titan's atmosphere is mostly nitrogen, but it also contains methane. On Titan, liquid exists on the surface, not as water, but as lakes and seas of liquid methane and ethane. These hydrocarbons rain from the sky, carve river channels, and collect in vast basins. Titan is the only place besides Earth where we confirm stable surface liquids. Another remarkable moon is Enceladus. Though only about 313 miles wide, it ejects towering geysers of water ice from its south pole. These plumes originate from a subsurface ocean. When the Cassini spacecraft flew through them, it detected organic molecules, the building blocks of life. Enceladus is now considered one of the most promising places to search for life beyond Earth. Uranus is different from any other planet. Its axis is tilted by about 98 degrees, causing it to roll around the sun on its side. One pole experiences continuous sunlight for 42 years, followed by 42 years of darkness. The most likely explanation is a massive collision early in its history that knocked the planet over and distorted its magnetic field. Neptune lies even farther out, taking 165 Earth years to complete one orbit. Since its discovery in 1846, it has completed fewer than 2 full trips around the Sun. Neptune has the fastest winds in the solar system, reaching speeds of up to 1,200 miles per hour. Massive storms form and disappear unpredictably. Voyager 2 observed the Great Dark Spot in 1989, but when astronomers looked again years later, it had vanished. Beyond Neptune lies the Kuiper Belt, home to countless icy remnants of the solar system formation. Pluto is the most famous of these objects. Once considered the 9th planet, Pluto was reclassified in 2006. Though small, only about 1,473 miles across, it's a complex world with mountains of water ice, plains of frozen nitrogen, and a thin atmosphere. Pluto and its largest moon, Charon, orbit a shared center of gravity, making them a true binary system. Far beyond the Kuiper Belt lies the Oort cloud, a vast, spherical shell of icy objects extending nearly 2 light-years from the Sun. No object from the Oort cloud has ever been directly observed. We know it exists because long-period comets originate there. This distant region marks the true edge of the Sun's influence. And within all this immensity, Earth is just one small rocky world, orbiting quietly at a distance of 1 astronomical unit. Now, let's leave the solar system entirely. Beyond this point, distances grow so vast that ordinary measurements lose meaning. The nearest star system, Alpha Centauri, lies more than 4 light-years away. Even our fastest spacecraft would take tens of thousands of years to reach it. As we continue outward, through our stellar neighborhood, across the Milky Way, and into the larger universe, Earth doesn't just become small. It disappears. Together, astronomers call this region the local group. This is our immediate cosmic neighborhood. The largest member of the local group is Andromeda, also known as M31. Andromeda contains roughly 1 trillion stars, more than twice the number found in the Milky Way. It stretches about 220,000 light-years across, making it more than twice the diameter of our galaxy. Andromeda is also moving toward us. In about 4.5 billion years, Andromeda and the Milky Way will collide and merge into a single, enormous galaxy. There's no need to worry about this collision. When galaxies merge, the stars inside them are so far apart that actual star-to-star collisions are extraordinarily rare. The 2 galaxies will pass through one another, their gravity slowly reshaping their paths. Over time, they will settle into a single large elliptical galaxy. By that time, the Sun will likely be long gone. Humanity, if it still exists at all, will either have left Earth or disappeared entirely. The next largest member of the local group is the Triangulum Galaxy, also known as M33. It contains around 40 billion stars and spans roughly 60,000 light-years. Smaller than the Milky Way, but still a respectable galaxy in its own right. The rest of the local group is made up mostly of dwarf galaxies, small collections of a few billion stars or fewer. The Large Magellanic Cloud, which orbits the Milky Way, contains about 10 billion stars. The Small Magellanic Cloud contains only a few billion. From the southern hemisphere, both appear as faint, fuzzy patches in the night sky. The local group spans about 10 million light-years. That distance sounds enormous, and it is, but it's only the beginning. The local group itself is just a small part of a much larger structure known as the Virgo supercluster. This immense collection of galaxy groups and clusters stretches roughly 110 million light-years across and contains at least 100 galaxy clusters, with a total of around 100 trillion stars. At the heart of this supercluster lies the Virgo cluster, located about 54 million light-years from Earth. This cluster alone contains between 1,200 and 2,000 galaxies. Some of these galaxies are far larger than the Milky Way. One of the most remarkable is M87, a giant elliptical galaxy near the center of the Virgo cluster. M87 contains about 1 trillion stars and is roughly 120,000 light-years across, similar in size to the Milky Way, but much more massive. M87 is also famous for something else. In 2019, astronomers released the first-ever image of a black hole. That image showed the shadow of the supermassive black hole at the center of M87, with mass about 6.5 billion times that of the Sun. Take a moment to consider that scale. The Milky Way feels enormous, but it's only one galaxy in a cluster that contains thousands. And that cluster is only one part of a supercluster containing hundreds of clusters. If the Milky Way were the size of a coin, the Virgo supercluster will be the size of a large city. Everything we've talked about so far, the Sun, the solar system, the distances between stars, the entire Milky Way, would fit onto that single coin. And Earth would be smaller than anything you could see with a microscope. In 2014, astronomers discovered something even larger. They realized that the Virgo supercluster is itself part of an even more massive structure called Laniakea. The name comes from Hawaiian and means immeasurable heaven. Laniakea is a supercluster of superclusters containing around 100,000 galaxies spread across 520 million light-years. All of these galaxies, including the Milky Way, are slowly flowing toward a central gravitational region known as the Great Attractor. The Great Attractor lies hidden behind the dense dust and gas of the Milky Way, blocking it from direct view. For decades, astronomers could detect its gravitational influence without being able to see it. By observing the universe in radio waves, infrared light, and X-rays, scientists eventually pieced together the picture. The Great Attractor isn't a single object, but a region containing multiple massive galaxy clusters, including the Norma cluster. But even this isn't the end. Beyond Laniakea lies the Shapley supercluster, about 650 million light-years away. It contains thousands of galaxies and has a total mass of roughly 10,000 trillion times the mass of the Sun. Its gravity appears to be pulling Laniakea and everything inside it toward it. At this scale, the Milky Way becomes just one galaxy among 100,000, and Earth vanishes entirely from relevance. When astronomers map the universe, a pattern emerges. Galaxies are not scattered randomly. They form vast filaments and walls, creating a structure known as a cosmic web. Between these filaments lie enormous empty regions called voids. This structure formed because of tiny density variations in the early universe. Over billions of years, gravity amplified those differences. Dense regions became denser. Empty regions became emptier. The result is a universe where most of space, about 80% of it, is nearly empty. One of the largest known structures is the Sloan Great Wall, stretching about 1.37 billion light-years. Another, the Hercules Corona Borealis Great Wall, may extend nearly 10 billion light-years, challenging our understanding of how such massive structures could form. Between these vast walls are the voids. The largest known void, the KBC void, spans about 2 billion light-years. From its center, the nearest major galaxies would be a billion light-years away. The universe would appear almost empty. At the scale of the cosmic web, Earth doesn't just become invisible. It becomes inconceivable. And yet, this tiny planet, lost in an ocean of emptiness, is the only place we know where life exists. Now, let's take one final step back. Beyond the walls and filaments of the cosmic web, the universe continues, smooth, dark, and nearly empty. On the largest scales we can observe, matter spreads out evenly, fading into a quiet background of space and time. This is the observable universe. The observable universe has a radius of about 46.5 billion light-years. That means the diameter, the full width, is roughly 93 billion light-years. This number already feels impossible, but it hides something even stranger. The universe is only about 13.8 billion years old. So how can we see objects that are more than 46 billion light-years away? The answer lies in expansion. Space itself is stretching. As light travels through the universe, the space between galaxies continues to grow. So while the light began its journey much closer, the distance it had to cross increased while it was traveling. Light didn't just move through space. Space moved with it. This is why distant galaxies appear redshifted. Their light is stretched to longer, redder wavelengths as space expands. The farther away a galaxy is, the faster it appears to be moving away from us. Eventually, there's a limit. Beyond a certain distance, galaxies recede faster than light, not because they are moving through space faster than light, but because space itself is expanding too quickly. Light emitted beyond this boundary will never reach us. That boundary is called the cosmic horizon. Everything we will ever see, every galaxy, every star, every flash of light, exists inside this horizon. And beyond it, there may be more universe, perhaps infinitely more, but we will never know. Now, think about what a light year truly represents. A light year is not just a distance. It's a measure of time and travel combined. When you look at the sun, you see it as it was 8 minutes ago. When you look at Jupiter, you see it as it was about 40 minutes ago. When you look at Saturn, you see it over an hour in the past. When you look at the nearest stars, you're seeing light that left them years ago. When you look at distant galaxies, you're seeing light that began its journey millions or billions of years ago. Looking deeper into space is the same as looking deeper into time. Some of the faint galaxies captured by the James Webb Space Telescope appear as they were just a few 100 million years after the Big Bang. Their light has been traveling for more than 13 billion years before reaching Earth. Those photons cross expanding space, avoided stars, dust clouds, and black holes, survived cosmic radiation, and arrived, finally, on a tiny planet, hitting a mirror built by intelligent life. All of that effort, so we could look up. Now return your attention to Earth. Earth is about 8,000 miles wide. It orbits the sun at a distance of 1 astronomical unit. The entire solar system, including the distant Oort cloud, spans about 2 light years. That means everything humanity has ever known exists inside a sphere of space 4 light years across. Beyond that sphere are stars. Beyond stars are galaxies. Beyond galaxies are clusters. Beyond clusters are superclusters. Beyond superclusters is the cosmic web. And beyond the cosmic web is silence. The light year exists because ordinary units fail. Miles fail. Kilometers fail. Even the width of Earth, the size of the sun, and the span of our galaxy eventually fail. Only time, expressed as light traveling through space, remains useful. A light year is how the universe tells us how far something truly is. And when we finally understand that, something subtle happens. Our sense of importance shrinks, but our sense of connection grows. Because every atom in your body was forged in ancient stars. Every element heavier than hydrogen and helium was created in supernovae that exploded billions of years ago. The universe didn't just happen around us. We came from it. So when you lie back tonight and let your thoughts drift, imagine a single photon of light, leaving a star, crossing a light year, then another, then 1,000, then 1,000,000,000, until it reaches you. That journey, quiet, patient, and unimaginably long, is what a light year truly means. And in that understanding, the universe stops feeling distant and starts feeling infinite. Good night.